Okay, Gen Chem kids, we are going to do some more Lewis structures today. So remember, when you draw a Lewis structure, we have to, one, know all the valence electrons for all the atoms that are in that molecule. And we have to count them up and we have to add them all together. Two, then we've got to decide what's going to be in the center. And then we've got to satisfy everyone's octets, all the atoms' octets. Or if it's hydrogen, they just need 2 electrons. And then we've got to count all the electrons that we've used, and hopefully they match what we have. Today we're going to start layering in double and triple bonds on this and how we use those to satisfy octets while using fewer electrons. And we're also going to start layering in ions and how we do Lewis structures for covalently bound ions. So here we go. We're just going to dive into it today. So multiple bonds, here we go. Sometimes atoms can share more than one pair of electrons. And when they share more than one pair of electrons in a single bonding area, that's called either a double bond, if they're sharing 4 electrons, or a triple bond. Sometimes they can share 6 electrons in a single bonding area. So let's go figure this out. We're going to start with oxygen. Oxygen right here, when oxygen is the oxygen in our atmosphere, it comes in groups of 2. It's what we call a diatomic molecule. So let's look at oxygen on our periodic table. And when I see oxygen on my periodic table, I see that it's in group 16, so that means it will have 6 valence electrons. So that's where I'm going to start. Oxygen has 6 valence electrons, and I've got 2 oxygens because of that subscript 2 there. So that means I'm going to have 12 valence electrons that I can use. Okay? Now, because I only have 2 oxygens, I really don't have a center atom, so I don't have to really worry about that. So here we go. Let's put a single bond in. And if I put a single bond, if you remember, that single bond is 2 electrons. So that means each of these oxygens have 2 electrons that they can use. To have the octet, though, they need 6 more. So let's put in 3 lone pairs on each of these oxygens. Okay, so if I've put in 6 electrons or 3 lone pairs on each of these oxygens, I now have 8 electrons total for each of these oxygens. Let's count how many electrons I have used, though. I've used 2, 4, 6, 8, 10, 12, 14 electrons. That's 2 more than I have. I only have 12. So my question is, how do I satisfy oxygen's octet while only using the 12 electrons? So what I'm going to do is I'm going to put a double bond in here. So if I put a double bond in here, that means I'm sharing 4 electrons between those 2 oxygens. So that means I only need 4 more electrons for each of these oxygens to have their octet. So I'm going to put in 2 lone pairs on each of these oxygens. And that will give me, let's check my oxygens here to make sure I have a full octet around each. 2, 4, 6, 8 around the one on the right, and 2, 4, 6, 8 around the one on the left. So I'm good. Let's see how many electrons I've used, though. Let's change color again. I've used 2, 4, 6, 8, 10, 12. So I've used 12 electrons. So this indeed is going to be our Lewis structure for oxygen. Oxygen is double bonded. Okay, so this is what's called a double bond. It means I'm sharing 4 electrons. Let's look at carbon dioxide here. So let's look at carbon. Carbon's right here is in group 14, so that means that I have 4 valence electrons. And oxygen, once again, here in group 16 means that I have 6 valence electrons. So let's look at doing carbon dioxide. So carbon has 4, oxygen has 6, and I've got 2 oxygens. So 4 plus 12, 4 plus 12, that gives me 16 valence electrons total to use. Okay. Now, the next thing, we do have 3 atoms, so we do need to figure out what's going to be in the middle. Remember, we put the least or the less electronegative atom in the middle. So oxygen is much closer to fluorine than carbon is. So carbon's less electronegative, so we're going to put carbon in the middle. Okay, so let's put carbon in the middle. So if I put carbon in the middle and do single bonds to each of these oxygens, the oxygen on the left has access to 2 electrons from that bond, so it needs 3 more for its octet. Whoa, that really didn't want to draw. And let's try that again. Let's erase that. Let's make it a little bit easier to see. So 3 lone pairs or 6 electrons on each of these oxygens to satisfy their octets. Okay, now carbon in the middle has 2 bonds going to it, so that means it has 4 electrons that it can use. So it needs 4 more. So I'm going to put a lone pair on top and a lone pair on the bottom. Okay, let's count these electrons that we're using. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. I have used 4 more electrons than I really have. So if you noticed in our example last time with the oxygen, each double bond saves us 2 electrons. So I need to save 4. So I need to put in 2 double bonds here. So I'm going to put 2 double bonds. I'm going to put 1 to each oxygen. Okay, so if I look at each of the oxygens, they have 4 electrons. They need 4 more. So I'm going to put 2 lone pairs on each of the oxygens to satisfy their octets. And carbon has 4 bonds going to it. And each of those bonds is 2 electrons. So 4 times 2 is 8. That means carbon's already full. So let's count the amount of electrons that I have used. I've used 2, 4, 6, 8, 10, 12, 14, 16. That's exactly the amount of electrons that I have. So this is indeed the Lewis structure for carbon dioxide. All right, so let's look at this. I want to talk about that center atom, that carbon. So double bonds are actually considered one bonding area. So when you look at this area, or this center atom, you're going to say that it has 2 bonding areas. Because double bonds are considered one bonding area. Okay. Why is my Hudley camera installing? I already have it installed. Okay, so let's go on to carbon monoxide. Carbon, we already looked up before. Carbon's got 4 valence electrons and oxygen has 6. So our grand total between these two is 10. I've got 10 I've got 10 valence electrons total here. Okay, so I only have 2 atoms here, so I don't really have to think about what's going to be in the middle. So I'm going to draw carbon with a single bond to oxygen. The carbon has access to the 2 electrons in the bond, so it's going to need 6 more for its octet. And same with oxygen. It has the 2 electrons, so it's going to need 6 more for its octet as well. So if I look at that, I have used, let's see, 2, 4, 6, 8, 10, 12, 14 electrons. I only have 10. Now, we said that a double bond saves us 2 electrons. I need to save 4. So what can I do to save 4 with only 2 atoms? Maybe I could try a triple bond? Let's try that. Let's change our color. Let's try a triple bond. So if I do a triple bond, which means I'm sharing 6 electrons between that carbon and that oxygen. So the carbon has access to 6 electrons in those bonding electrons. So it needs 2 more for its octet. And the oxygen also has 6 electrons in those bonds. So it needs 2 more for its octet. Let's count how many electrons I've used here. I've used 2, 4, 6, 8, 10, which is exactly the amount of electrons that I have. So carbon monoxide is indeed triple bonded. Okay, now let's move on. We have hydrogen cyanide, also called cyanic acid. So we've got hydrogen to look at, and we've got nitrogen to look at, and we've got carbon to look at. So hydrogen, first column, 1 valence electron. Nitrogen, column 15, so 5 valence electrons. And carbon, 4 valence electrons. So let's put those in. So hydrogen has 1 valence electron, carbon has 4, and nitrogen has 5. So if I add up 1 plus 4 plus 5, that gives me a grand total of 10. Okay, now let's see, what are we going to put in the middle? Of hydrogen, we can't put hydrogen in the middle because hydrogen never goes in the middle. We've got to choose between carbon and nitrogen. Now, nitrogen is more electronegative. It's closer to fluorine. So we're going to choose carbon to go in the middle. So we're going to put carbon in the middle. All right. So remember hydrogen can only do 2 electrons. So hydrogen with that bond with carbon is already done. Okay? Carbon has 2 bonding areas, meaning it has 4 electrons that it's using. So I need to put 4 electrons there to fill up carbon's octet. And nitrogen has 1 bond, so it has 2 electrons. So it's going to need 6 more, or 3 lone pairs, to fill up its octet. Now let's count how many electrons that I have used in this picture. I've used 2, 4, 6, 8, 10, 12, 14. I only have 10 to use. Now, double bonds will save me 2 electrons, but I can't put in 2 double bonds, which I would need to do to save the 4 electrons that I need to save, because hydrogen can only make 1 bond. So double bonds are not really an option here. The only thing I can do to save the 4 electrons that I need to save is putting in a triple bond between the carbon and the nitrogen, because the hydrogen's already full. So I'm going to try that. Okay, so if I do it that way, the hydrogen's already full because it's got the 2 electrons from that bond. Carbon has 1 on the hydrogen side, 2, 3, 4 bonds when you count the triple bond from the nitrogen side. So carbon already has access to 8 electrons with the 4 bonds because each bond is 2 electrons. And nitrogen has 1, 2, 3, 4, 5, 6 electrons with the triple bond. So it just needs a lone pair to satisfy its octet. Now let's count up the amount of electrons that we have used and make sure that it is indeed only 10. So I've used up 2, 4, 6, 8, 10 electrons on this. So yeah, this is the Lewis structure for cyanic acid. Hydrogen is single bonded to the carbon and carbon is triple bonded to the nitrogen. That is the Lewis structure. Okay, now in this Lewis structure, since we do have a center atom, let's look at carbon. Triple bonds are also considered a single area of bonding. So we would call this 2 bonding areas. And notice there are 0 lone pairs on the carbon. Okay, same with the carbon dioxide, 0 lone pairs.
Hey.
Hey.